Tiens, il y a là.
Alors
Sur les documents. Faut que je change. Je suis très belle de conférence.
Je peux l'imprimer. Hein.
Ah, tu peux réimprimer?
Ouais.
Ouais, ce sera mieux.
Je vais mettre.
Le professeur des universités.
En fait, c'est.
Autrement, je peux pas être.
Autrement, tu ne peux pas être président.
Non.
Mais moi, je suis pas non plus. Moi, je suis pas non plus. Si tu changes, moi, je ne suis pas professeur de l'université.
En fait, moi aussi,
je suis directrice de
Mais oui,
recherche.
toi, t'es directrice de recherche.
Ah là là, je sais pas.
Donc, tant qu'à faire, si tu changes des trucs,
On change tout.
tu changes tout. Il faut demander aux autres s'ils disent.
Est-ce que Nathanaël, t'es bien chargé de recherche?
Oui, ça, c'est pas changé.
Ah, université, Sorbonne, université. C'est ça.
Et souvent,
Oui, c'est pareil, tu vois,
il y a marqué tout université, 2 points. Et en fait, le nom officiel, c'est pas la même ville, c'est la Sorbonne, mais
Sorbonne université, ouais, c'est bien.
Moi, ils m'ont mis l'école centrale de Nantes.
Je discute, hein. Qu'est-ce que c'est? Qui t'a changé? Et je suis pas université de Rennes non plus.
Les autres, ils ont CNRS.
Il n'y a rien qui marche.
Moi, CNRS, ce serait pas mal aussi, puisque
Il n'y a rien qui marche.
puisque vous avez le droit à CNRS.
Il n'y a rien qui marche. Enfin, je fais comment je Alors, c'est quoi? Ah, t'es une salle. Ouais. Chargé de recherche. Sorbonne Université.
Il est sûrement CNRS, parce que Sorbonne Université, mais c'est envie de Sorbonne.
Ah non, mais tu veux que je mette CNRS ou Sorbonne Université?
Tout sur l'université, je pense.
Ok. Et là, c'est pareil, donc il faut tous les refaire.
Ouais, donne-moi une et je vais faire.
Voilà.
Il n'y a pas. J'ai dit l'erreur sur moi aussi, donc moi j'ai changé, mais je ne veux pas.
Après, c'était quoi?
C'était écrit Université de Rennes. Ça, j'ai changé parce que.
Parce que tu savais que c'était toi.
Ça, j'ai pas vraiment regardé parce que je sais qu'il m'a dit.
Bah oui, donc
Surtout il y a 2 fois là.
ça va bien se passer. C'est une magique c'est robotique.
J'ai fait la liste.
Quel est le nom de votre équipe?
Rainbow.
Ah, Rainbow, d'accord.
C'est une magique.
C'est ça.
Je crois que je fasse.
Ça aurait fait quelque chose pour les étudiants.
Attends, s'il y a des gens qui se connectent à Lisa. So you are sharing your presentation?
Yes. Ready to start or not? No.
You want to start?
I think.
Okay. We start. So, so thank you for all for being there. Just a pleasure to be here to listen to your PhD defense. So, Lisheng Kuang, entitled Ungrounded haptic interfaces for guidance and interaction rendering. So the jury here is composed of first two reviewers, so Mr. Lorenzo Masia, which is a professor at Heidelberg University, Nathanaël Jarrassé, who is a chargé de recherche in English? Researcher of CNRS. Madame Christine Chevallereau, which is also a researcher, senior researcher from CNRS too, and we have the two supervisors, so Mr. Paolo, Robuffo, Giordano, which is also a senior researcher at CNRS, and Claudio Pacchierotti, the researcher also at CNRS, not at CNRS here, and myself, Babel, so I'm a professor at IRISA. Not CNRS, sorry. And so you have 45 minutes for your presentation, and after that we will have some questions.
Okay, great. Thanks for the introduction. And okay, good morning. I'm Lisheng Kuang. Today I will present my research work across the past 3 years. And my PhD thesis centers on the development of haptic interfaces for human-machine interaction and human mobility aids. It is entitled Ungrounded Haptic Interfaces for Guidance and Interaction Region. And the ground objective is to advance the state of the art in this field of haptics, in this field of haptic research, and to achieve more effective interactions between our surroundings. So first things first, what is haptics? Well, haptic is an adjective of synonym to touch-based, which is originated from Greek language and simply means able to touch or grasp. And by analogy to acoustics and optics, haptic refers to the discipline that studies the sense of touch. And just as graphics and audios which touch humans' sight and hearing, haptic technology touch people's motor sensory system, the sense of touch. And haptic feedback is provided by the combination of cutaneous stimuli and kinesthetic haptic sensations. And on the one hand, cutaneous stimuli are detected by the mechanoreceptors in the skin and enable humans to receive the local properties such as temperature, texture, slippery, and vibration. And on the other hand, kinesthetic sensation provides the information about the velocity and the position of the neighboring body parts, including the force and the torque, and by the means of receptors in the muscles and joints. Well, when we talk about haptic technology, we refer to the capability of designing artificial systems that can perceive and transmit different pieces of information, and that human sense can perceive in a distributed and verbal and effective way. And for example, in virtual interaction, haptic technology enables human people to relocate their sense of touch at one place other than at their true location, and enabling virtually touch with the remote object through the action of one or multiple animators. Same happens in robotic teleoperation, where haptic technology again enables the human operators to relocate their sense of touch, and through the action of one or multiple remote operators. Here we can say remote operators. Here is the remote robot here. So indeed, haptic technology and interaction enable the virtual interaction and the remote environment reading between humans and the objects. And in this context, haptic technology and actuation plays analogous role to video cameras and displays which register images and play them back to our eyes, and microphones and speakers which register sound and play them back to our ears. So what is the representative grounded haptic interfaces? So let's say textile haptic interfaces. So this kind of device provides force sensations to the body through the end effector, like a pen or sphere or a symbol held by the user. And they have a base which lies on the external supports such as the table. And the promising approach to improve the portability of this kind of device is to move the base closer to the body parts of the application. And ungrounded handling interfaces pick up this challenge by moving the base onto the body of the user. So wearable handling interfaces and handheld handling interfaces are the representative ungrounded handling interfaces. And from the state of the art, we have learned that it is not possible to achieve a device which can perceive all the range of sensations and then human sensing touch can perceive in a distributed, comfort, and wearable manner. And so, in this context, I have moved forward in my research to understanding the best compromise between the effectiveness and the design constraint. So, which means how to achieve the best effective information and interaction flow in with the smallest design and the most comfortable wearability. So the objective revolves around the need and the requirement about the design of this kind of interfaces. And I follow the recommendation provided by my advisor Claudio here. So which from their real work, and which says for wearable handling devices, the design should be considered including the form factors, weight, impairment, and the comfort, and which also some other criteria like pendant mapping and recognition load should also be considered into consideration for navigation and interaction rendering. And I will present my contribution in the fourth set. The first contribution describes the design of a wearable continuous device for position and location handling feedback and for human navigation. And the second describes a few handles for motion guidance, teleportation, and in-chronotype handling interaction. And the third one describes a two wearable device from one design for the palmar-based interaction. And the final one describes the handheld wearable tactile device to study the effect of haptics during fine motor skill training. And the first contribution presents a 2-degree freedom wearable device which could provide position and location handling feedback to multi-body parts and for human indoor navigation. And it is designed to be wear on the forehead, the arm, and the back of the hand. And the device is composed of a cartesian-like structure. Here you can see on the right, on the left, and driven by two linear motors. It has a workspace of 12 times 12 millimeters. And at the intersection of the guide, we fix the cylindrical pin which is indenting to the skin. And a metallic sphere is also housed at the end of the pin in contact with the skin. And we have a spring in the spring between the sphere and the upper point to make sure that the constant contact should be provided between the sphere and the skin. And first, we calculated the different threshold in providing skin strength sensations of the device. And 5 participants were asked to wear the device and to recognize the difference between the two provided skin strength stimuli of the device. And the result shows that the forehand shows the base recognition rate and for all the positions, followed by the back of the hand and the forearm. And we also calculated the performance of the device in rendering different shape patterns. And these 5 shape patterns are generated by moving the pin around the skin in a continuous movement when the device is worn on the forearm and the back and of the hand and the back of the hand. The results show that shapes were quite easy to recognize for all the 3 positions, and especially an horizontal line which is the easiest to recognize. And finally, so we mentioned that the device is for navigation. So we use the device to provide directional cues for 6 subjects to work in an indoor space. The experiment was carried out in a 4 times 5 meters room, instrumented with 12 optical cameras to track the real position of the user in real time. And the subject wear the device on the forehead and follow the guidance cues as closely as possible. And the pin with the device move left and right proportionally to the error in the tracking with respect to the target path. And at the end of the task, we also provided a sequence of random 3 shapes for the participant to recognize, which can be, for example, indicate a task for the operator to complete. And the error in tracking the tragedy was calculated between the distance of the user and the target and the closest point on the target path. And we compared 3 different target paths, and the users where the device goes through all the paths. The result showed that the device was able to take the subject through all the target paths with an area of 0.26 meters, and also recognizable shapes are provided in the end of each path. And this contribution presents a wearable coordinates device which could be worn on the forehead, the arm, and the back of the hand for providing skin stretch and location feedback for human navigation. It is lightweight, inexpensive, and easy to use, and coming in a compact factor. And however, the result of the experiment and also the qualitative result from the participants reveals that it is not quite reliable for using the skin stretch feedback to provide navigation cues to humans, especially when the device is one of the forehead, which will quickly make the wearability uncomfortable. And also, it's important to know that in order to provide the effective skin stretch, the device needs to be strongly tightened to the forehead, which also makes the contact between the device and the human uncomfortable. And so for this reason, I moved to the design of a series handles to provide similar information, but to the hand. And this part of my thesis was inspired the collaborative project called Donald, funded by here. So which objective is to provide or to develop a versatile handle which can be used for providing humans with navigation information and to be used for powered mobility aids such as walkers, keys, and one keys. And in this work, we present a handle which can be used both in grounded and handheld configuration, able to provide position and kinesthetic feedback to the hand. So the device consists of a lower platform and the upper platform, which the upper platform moves on the surface of the sphere. And the 2 platforms are connected with 3 legs, each having a spiral curved link. And the 2 ends of each link are connected with 2 series revolving joints, forming a coupling parallel mechanism which can move freely in 2 degree freedom according to the constraint and force on each leg. And the graph dot on the top shown here is the surface of a sphere for which the upper platform moves. And then we also installed a spherical camera on the top of the upper platform, which makes the interaction with the hand and the device more comfortable. And so we also analyze the mobility of the device and to see that, so as you can see from here, the upper platform moves on the surface of the sphere as we mentioned, according to the constraint and the active force on each leg. And compared to standard serial mechanism, the parallel mechanism can provide fast dynamic and high payload with relatively small size and low weight. And of course, a large range of motion can be obtained by choosing appropriate dimensional parameters and the different actuations. So based on the same mechanism, we created 2 versions of the device with different dimensions and including a not a biaxial module to register the user input. And this joystick-like module is important because the device itself is not bang drivable. So as I mentioned before, the device can also be used as a handheld configuration, as you can see from the video on the right. And based on the mobility analysis, we also analyze the kinesthetic of the device to find the relationship between the motors and the motion of the upper platform with respect to the lower one. And similarly, we do some evaluation with on the device, and to find the performance of the device in providing navigation information to the user. And first, we test how easy for user to recognize a certain target motion path rendered by the device. And we divided the experiment into two parts. The first part on the left, we make the device to render a series of 8 linear patterns. And on the second part, the device rendered 3 shape patterns. And in the experiment, the device is used in its grounded configuration with the lower platform attached to a table. And the subject are seated in front of the device and place their dominant hand on the upper platform. And so in the first part of the experiment, the device generates a series of linear patterns. The center of the upper platform moves on the surface of a sphere, as we mentioned before, which is the workspace. And each linear pattern starts from the left side, the resting position in the center, and then moves to the relative position like E or west, and then back again to the resting position. And the results are present in the confusion matrix, which shows the percentage of the recognition rate of the rendered and the recognized patterns. And as you can see from here, the east and the west was easiest to recognize for along all the shapes. And and all the rates were above chance level. And in the second part of the experiment, we asked the device to move along 3 shape patterns. And these patterns are uncharted over the surface of a sphere, just similar as before. And the results show that the square patterns, which make a squares on the top, was the easiest or the hardest to identify. But in general, all the shapes generate very good shapes and with a very high recognition rate. And to enable the user to provide inputs, the device can also be used both in its grounded configuration and integrated with the biaxial local module. So in this case, the device itself can provide kinesthetic feedback to the hand, and the local module can enable the user to provide some command cues to the external platform, such as a wheelchair on the right here, or for robotic teleportation in some other cases. And this bidirectional version of the device enables the handle to provide directional guidance feedback to the hand, and also two-channel control command from the local module to the external system. And the use of the local module also requires much less effort with respect to using a backdrop impedance-like device, which might be quite comfortable for our users to use and for the target applications. And as such an example here, so when we put the device on the powered wheelchair, the device can provide directional guidance, kinesthetic feedback to the hand, and the user can control the powered wheelchair through the biaxial module. And inspired by the same designer, we modified the design to include 2 shapeable end effectors on the upper surface to generate a different range of encounter-type haptic interactions. So we achieved the design of a 3-degree freedom shapeable device for encounter-type haptic interaction. And as you can see from the left, the main structure of the device with no end effectors attached to it. And the base platform was attached to an external table in its grounded configuration. And the upper platforms moved on the surface of the sphere, just as the previous handle we showed before. But this time, the 3 articulated legs are connected to the upper platform through 3 joint bases. which is actuated by the motors through the spiral cam. And we also considered two end effectors to attach to the joint base through the 3 joint sliders. So which can move towards or forward, towards or out of the center of the upper platform. And as a representative example here, we consider 2 end effectors. The first one is soft end effector, which can change its curvature. And the second one is an origami-inspired end effector, which can change its shape from flat to a sharp edge. And the first end effector we consider here is the soft Y-shaped strip attached to the joint sliders, and it is composed of a 3D printed flexible strip attached to the upper platform on the joint sliders. When the spiral cam rotates, the diameter of the circle here can change, and so control the shapes of the end effectors. So as we can see from the video here, the end effector is able to change its shape in both the bending state and in the straight state. And all the curvatures are also changed when the spiral cam rotates. The second end effector we consider is an origami-inspired end effector. So it is composed of a series of triangular panels, you can see on the left, and which can be jointed and form a modular recoverable surface. And such a surface can generate different shapes like a vortex and edge, or even a flat surface on the sideways. And we also carried out a user study to evaluate the rendering capabilities of the soft end effectors to see how is it possible to render different spherical cams with different curvatures. And we considered 40 groups of comparison using 2 alternative force choice, and each repeated twice. And as expected, as you can see on the left, when the difference between the 2 curvatures increases, it is getting easier to recognize which one has a larger curvature. And this result provides us useful insight regarding how to control the device. And we also present a user study case where participants interacted with the virtual object in a 3-dimensional environment. And the users also wear the HTC Vivid tracker on the wrist to track the position of the hand, and also the device is attached to a table in its grounded configuration. So this is just a representative example of how the device can be used, just as shown in the video here. So the user can interact with the surface with different curvatures, or the smaller one or the large one. Also, the device follows the hand when the hand is moving. And this handle merged and used the 2 main concepts of haptic interaction and technology. So encounter time interaction and handheld feedback. So in my work, I move forward and in both of these 2 directions, designing a wearable encounter handling device for the PAM and a handheld device for fine motor skill training. And taking advantages of the great group of wearable haptics, as well as the short research experience I spent at Oxford University, I applied my findings for the development of a serious wearable encounter time handling device. And in this respect, I worked on the 4 degrees of freedom wearable handling device for haptic reading of surfaces and edges. And the device is composed of a static upper body attached to the back of the hand and a foldable 2-piece end effector in contact with the PAM. And articulated legs are composed of articulated and straight links. And 4 motors, 2 on the upper body and 2 on the arms, actuate the end effector and control the movement of the device. So we also did mobility analysis. As you can see from here, the two planar level chains actuated by the 4 motors move the end effector of the device and control the movement within the XY plane here. And the position of the cylindrical bearing of the end effector and the raw angle theta of the end effector with respect to the XY plane, and also the alpha or the folding angle on the effector defines the movement of the device of the end effector on the device. And this 4 degrees freedom can be represented by the 4 movements shown below here. So the first 2 are vertical and horizontal movement with the device with the end effector fold or unfold, applying pressure and skin strength sensations through a flat surface or a sharp edge. And the third one, a fold or unfolding movements of the end effector, providing the sensation of interacting with different edges. And the final one with a rolling movement, providing the sensation of interacting with a slanted or uneven surface. So we also tested the capability of the joints on the device to follow a series of position and orientation target reference, and implementing using this simple closed loop control system. And each joint are actuated separately with the other joint free to move. And each motion are repeated 10 times, and the result are averaged. The results show a good tracking performance for all the joints. And we also evaluate the performance of the whole device with a more complex set of movements, also implementing the position control system. And we compared 5 target motions, as we can see from the left, also implementing the control method, and the results show that the device is able to follow all the control commands with a reasonably low error rate. And similarly as the 2 other devices, we also did a human subject experiment to evaluate the capability of a device in delivering haptic sensations in virtual immersive environments. So the users are store the device on the hand and recognize a series of pre-computed device configurations spanning all the rendering space along the 4 controlled variables. The results of the anti-recognition rate were well about translatable, especially for the slanted surfaces and the curvatures. But on the other hand, vertical movement is found harder to recognize, which can be explained by the fact that the control of the force applied to the panel is more important than the displacement. But this is something that we did not consider yet in our current approach. Yeah, we had a lot of fun working on this device, and it motivated us to go a bit further in its development. And we then extended its design to support multiple end effectors, with the idea that for a certain interaction and environment to render, the device should be able or should be ready to support the action of a wide range of haptic stimuli. And as an example of what can be done on this device, we described 5 very different end effectors and able to stimulate the sensations of interacting with the first one, slanted surfaces for providing the pressure and the skin stretch, and the second one, the soft U-shaped end effector providing different curvatures, and the third one here, a flexible surface with different stiffness and rotations, and the fourth one here is origami end effector with different local patterns. And finally, the fifth one here, we have a flexible texture with different grades on it to apply the different roughness and local properties. And of course, based on the structure here, you can see more end effectors can be designed to according to the interaction and the environment to render. And we also extend the kinematic analysis based on the previous device to account for the genetic nature of the control on different end effectors, and to enable the easy definition of different control parameters, control algorithm to apply it on this device. Yeah, the second device we consider here is composed of a flexible rectangular strip. It can be actuated by the combination action of the two arms, and the motion is constrained within the XY plane here. So as we can see from the video here, the device is able to generate different curvatures when the two arms move closer or farther from each other. Sorry. Now I'll show how to use haptics to drink water with a table, or with the bottle. The third end effect is composed of a flexible structure of Nantes rubber, so actuated by the combination action of the two arms. And the end effector can stretch and roll and apply different stimuli to the contact surface, such as the pen. And we also present the concept of an origami end effector and a texture elastic end effector. The former one is composed of a series of triangular shapes in whose edges can get more distant from each other when the end effector is stretched out. And it can apply different sensation of textures when you contact the surface. And the second one is composed of a soft elastic structure with small plastic grains attached to it. So when this end effector is stretched out, the distance between the grains will increase, so as to change the local properties and the roughness of the surface. And we also calculated the effectiveness of the device in reducing diverse contact interactions in immersive virtual reality. And the experiment, as a proof of concept, we considered the first three of the 5 end effectors. And the experiment was composed of a rotating cursor in the virtual reality, which provides 9 different objects for the user to recognize. And the user wears the device, and for each with each end effectors and for each object. And the 9 objects can be divided into 3 groups. And for the first groups, it consists of 3 objects having different edges. And the second group is composed of objects having different curvatures. And the third group is composed of objects having different stiffness. So as you can see from here, the participant interacted with each subject on the cursor using the wearable haptic device and equipped with all the 3 end effectors. And for each object and for each end effector, the participant will ask to answer the question. So how realistic was the interaction with this virtual object? The result shows that, as expected, the end effectors form significantly better when rendering the appropriate objects. For example, the E1 performed better when interacting with objects having different edges, and E2 when interacting with different objects having different curvatures, and E3 is better at rendering objects having different stiffness. And this result shows that it is quite important to tailor the end effector to the interaction at hand, supporting the need for modular input and the modular design of haptic interfaces. In parallel, I also worked on the design of a wiper tactile handle for fine motor skill training. And this part was also done in the short research period at University. And the objective is to investigate the relationship between the motor skill training in VR and haptic feedback and the psychological arousal. And to do so, we present the design and development of a motor skill training task along with a custom handle. which can be used as a haptic attachment to the geometric haptic device. And this work was carried out in my short visit at University with another student we call Uni. So my work here was, my work for this part was focused on the design of this handle. So my presentation will also focus on this aspect. And the task consists in moving a metallic loop through a wine without touching it. This is a very common task which can be used for evaluating the fine manipulation skills. And the task was carried out in a geometric loop and with a virtual loop in VR. And the feedback provides the undesigned contact between the loop and the wine. And the geometric touch device is used to provide a kinesthetic feedback, and the rubber tactile handle here is used to provide rubber tactile feedback. And by combining different feedback conditions and for different task environments, we were able to study the effectiveness for the learning of such fine motor skill training tasks. And for this part, as I mentioned, I developed a custom handle to provide vibro tactile haptic stimuli about the undesigned content between the wire and the loop. The device is shaped like an ellipsoid with the six haptic modules distributed around the main axis. And 4 of the vibro tactile modules are symmetrically distributed in the plane perpendicular to the main axis, and the other 2 are placed on the 2 ends of the main axis. And also we also designed a small gap between the haptic modules, which can help to weaken the transmission of the vibration from these motors, and making it easier to recognize the source of the vibration. For example, so we can see here, so when the vibrator L vibrates, the small gap can reduce or weaken the vibration transmitted to the other one we call U on the right. So we can recognize it is L, but not U is vibrating. And for this, we also carried out a perceptual experiment enrolling 12 participants. And the participant were asked to hold the device with all the palms spanning around the vibratile handle. And when the handle was actuated, each motor separately to generate the vibration stimuli. And the user will tell the experimenter when or where he feels the vibration. And the results show that the participants were able to correctly recognize the actuating motor in the experiment. And in general, the recognition rate is 68% when activating each of the 6 motors, and although 30% of them confused the actuating motors, as we said, the L and U here, and 80% of them confused the motors located farther away. Farther away means, for example, here the vibrators in F and the vibrators in B, so which means forward and backward. We also carried out a controlled experiment with 73 participants, studying the role of the 3 feedback conditions, including visual kinesthetic and visual vibratile and visual only. And this feedback provided the information about the undesigned contacts between the wire and the loop. And we want to study how is the performance and the improvement will be made based on these 3 feedback conditions. And the results show that the performance was improved in all the 3 feedback conditions. And along all the 3, after a training session as we expected, and the investigation into psychological arousal, including heart rate and electrodermal activity, also revealed that the training with kinesthetic feedback also resulted in higher arousal level compared to the training with vibratile feedback. And so in this including of haptic feedback, that's whose potential for motor skill training we are. although some other more work can be done to explore and study the trade-off between the kinesthetic and the cutaneous feedback, such as the vibration we used here. As a conclusion, so my thesis work has centers on the two primary areas of this kind of haptic interaction and technology, and range from the ungrounded haptic interfaces to facilitate haptic interaction and the examination of the haptic stimuli for navigation and haptic rendering. And the devices we developed have promoted us to delve into various design considerations, including mechanical mechanisms which can be used for generating the mechanical stimulation, and the actuation for actuating the mechanical component parts, and the sensors which can be used for carry and transmit the information, and some materials like rigid and soft to apply the contact with the contact surface, such as the skin. And we introduced the parallel mechanism which can be used to generate kinesthetic feedback, and we evaluated its efficacy in guiding hand motion. And we also proposed the origami-inspired end effector for applying a wide range of encountered haptic interaction, including the one with the multiple panels and the one with two panels here. And we also validated that flexible materials are able to generate the different sensation on interacting with shape and softness, both for the encountered haptic device and for the handheld device. And these diverse haptic interactions have been studied and have shown their effectiveness in rendering different interactions, both in VR and in real reality here. So we have validated that kinesthetic device can be used to wear on the forehead for generating position and location feedback, and for human indoor navigation. And kinesthetic feedback can be used for bilateral teleoperation, both on the powered wheelchair and some other cases like robotic teleoperation. And we also evaluate the effectiveness of soft materials for the implementing of different end effectors to apply the different softness and curvatures and the textures and the motions. And these materials have shown their effectiveness in immersive virtual reality, as we show here. And I would like to acknowledge the people who have worked with me during these years, including my advisors here, and also Francesco and Costantino and Uni from Aarhus University, and they worked with me for the short research experience. And also Mort here from IRISA and also in robotic group. And so also Marco Agravi here, and he was a postdoc here working with me and teach me a lot of practical techniques for including the robotics and haptics things inside. And also we have some two researchers from Monica and Domenico from Italy's University of Siena. Yeah, this is the last one. So the contribution-wise is have mostly published in haptic communities. But there's a strong potential for its dissemination of the result in different communities. Indeed, such research is highly interdisciplinary, and it requires knowledge from various areas, including automatic control and human-robot interaction and human perception. And all these disciplines must be contemplated in an integral perspective, leading to the insight of each of the aspects and the interaction between one another. And also opens very interesting opportunities for the cross-field interaction and collaboration. And finally, I like the multidisciplinary of this work and during my studies. And although sometimes it's quite difficult to work on this. Yeah, so yeah, thank you.
Thank you.
Thank you.
Thank you for the presentation. And let's start the question session. Lorenzo and Masia.
Okay, so thanks for the presentation. It's full of a lot of devices and ideas. I like them, most all of them. I have a few questions. Can you please go back to slide number 12?
Yes. Number 12. Boom.
Excellent presentation.
Yes, you're right. I should do this way. I will try. Yeah, 12. Right. So, yeah.
So can you comment a bit more, because I'm a bit lost. So the information in the slide is quite a lot. So these are just noticeable differences, and the 3-bar plot with 3 different colors corresponds to?
Different colors correspond to different.
So you have 1, 2, 3, 4, 5. This, I suppose, they are subjects.
I know. Yes, the subject and no. This 1, 2, 3, 4 to 11 means the displacements of the skin strength stimuli, and the colors means the different
the displacement.
Yes, we compare the difference between the two stimuli. Their difference is 1, 2, 3, or 4, 5 millimeters difference.
Okay, so I mean, I didn't see any dimension on the x-axis. Okay. Oh, okay. Range
Standard
Standard stimuli. Yes, it's a bit small here. And the color means the different position. So we can see from the left the light blue means the forehead, and the middle one means the back of the hand, and the other one, of course, for the forehead.
For a arm.
Yes.
And the lines orange, yellow, and green?
Orange or green also means the different positions. So we have blue, we have one.
Forehead,
No,
back, or the
the green one, yes.
So, I mean, what's the conclusion here?
So the conclusion here is that we calculate the different threshold between the two stimuli. So we can see from the key value here. So when the difference increase, it is easier to recognize the difference between the two skin strength parodies. So the first one, for example, between 4 and 5, and we first generate one with the 4 millimeter difference, and the second one is 5. So which means it's getting easier to recognize the difference between these two.
Why you didn't run two different force choices and then draw a psychometric?
Yeah, we didn't do that, but
because you used, I mean, the same approach in now I don't remember one of the 4 chapters, but you used basically psychometric function.
yes, we use that
If you
one.
would have used just noticeable differences, the 2 different force choices. You might have probably found what is the minimum threshold discrimination and draw a curve, basically 3 psychometric functions, and eventually you can compare them on the same plot for head, back of the hand, and for arm.
Yeah, probably. If we use that method, the result could be different, but we didn't consider this. So we didn't use the choice because we asked you to recognize either this one is bigger, either the other one. Otherwise, no. So they give another result.
Okay, one advice, because I mean, of course I read the thesis, but imagine you present the slides in a conference and you stay on the slides about 30 seconds. People get lost. I got lost. So in fact, I didn't understand.
Okay.
So we have to slow, but to be honest, so simplify, for example, the representation of the data, because it's quite graphical, but there's a lot of information.
Yes,
This is one small advice.
Yeah.
Slide 14, is this one is?
14, right?
Yeah, 14, wonderful.
14, yeah.
Okay. So can you comment a bit more on this confusion matrix that you drafted? Because, I mean, when you have percentage of recognition that is close to 50%, then it means there's a lot of, let's say, crosstalk between the different identification.
Yeah.
So if I see, for example, 72, 74, 7, but then I found 62. Recognition of the, for example, first plot for head that is actually the one that you used for the experiment on the forehead, if I remember. No, was the main experiment. And I had 62% classification for the triangular.
Yeah. Okay, for this one,
So do you think it's a high percentage or a low percentage of recognition?
that's why we use the horizontal line. We use the device to provide simply left and right, because this one we call the horizontal line. Again, the very best recognition rate with the first one 86 and 73, 78 and 86. So the shapes are more difficult to recognize, of course, and that's why we use the horizontal line. And this is might be mainly because that for the different shapes, triangular one and the rectangular ones, they're not quite similar, but sometimes similar for different persons to perceive. So that's why the rate is not super high than the simple line, because simple line is a line, but the other shapes, they have more movement, continuous movement.
But one question is, do you really need, with this haptic guidance, to render shapes like this?
Yeah.
Because that's the question. I mean, if you want to render displacement from a desired trajectory, that is, let's say, and you use the, if I understand, the proportionality of the, so you displace in a proportional way depending on the matching error with respect to the direction. Do you really need to render shapes, or you can use cardinal directions starting from the center point?
Yeah, that's correct. For navigation, yes, we don't need a complicated shape like this, because it will require more recognition load for the user. That's why we use the line, and we also use the shape, which could be used for as a target path. At the end of the target path, could be used for indicating certain target to complete.
What's the workspace of these things? It's about what, 2 centimeters, 3 centimeters?
It's 12. It's 12. No, it's 12 millimeters. Yeah.
12 millimeters, so 1.2 centimeters. So let's suppose that I should go straight, and at one point I deviate. The system will shift a bit, telling me, hey, you're deviating, or it's going on the other direction, just to tell me that I have to correct. But when it comes back to the center, the person will realize that I'm in a neutral position.
So what we did in the experiment is that we calculated the error between the position of the user and the target path. When the participant on the left, so the device the pin with the left, so to tell the user to go to the left. But when the participant goes getting closer to the path, and the device will also slowly go to the center. So that's why we did a training session to tell the user which one is the center position. So they will memorize this, so it's the center. And when the pin on the left or right, it is proportionally to the error between the user and the target.
But this is what I'm saying. So, I mean, if, for example, you deviate, you go with these things directly up to the left or to the right, and then you come back to the center, because more proportionality, if I look at the just noticeable difference that you showed, are not perceived by the person. And plus, I don't know if everyone recognized that the system present your sagittal plane. So there's a small deviation are not used.
Yes.
So are not perceived, also because you are walking.
Yeah. It's not always the same for different persons. But different persons have different perceptual capability.
And then another thing, so you run this just noticeable different in a static way. So I'm standing, and then what happens if I run the same experiment and you walk on a treadmill and you have vibration of the system on your head?
So we didn't try this way because
it's for walking.
Yeah, it's for walking.
So just noticeable difference. I mean, you can use just noticeable different or psychometric function with 2 forced choice, and then check what is the minimum threshold discrimination. But you should do it in a condition of usage, not standing. So when the person is walking.
Yes. So we didn't think about it, but it could be possible for the use to a treadmill. But
because I think that you will get, for example, discrimination threshold that is high.
It's possible. It's probably could be high, But as we know, for a robot device, when the environment is more dynamic, like we say more recognition things for the user to perceive, like the treadmill, when the treadmill is shaking and moving and tilting, so the user receive more information. So this will make the user to a bit more easier to perceive the feedback provided by the device. So the recognition
for me is the opposite.
Opposite.
Well, you have a disturbance. I mean, if you walk, you have a mechanical disturbance on your head because I mean, it's lightweight, these things, but I suppose that has a weight. With two actuators, give me a weight more or less. 100 grams?
We didn't do that, but it could be possible to try that.
Okay, so if you test on a treadmill, I'm pretty sure that you will have a discrimination threshold that will be slightly higher because it's in presence of a disturbance.
Might be.
It oscillates, basically, on the cadence of your step. So slide 16, you tell me when to stop, so. 16. Yeah. So, how this cognitive load test has been done? Because, I mean, what you do is asking the person to use the device in the motion tracking, motion camera room.
Yes.
And in the meantime, said, what kind of shapes is been drafting on my head? This is how it works?
Yes, this is done at the end of each pass in the blue circle here. So when the user around that point, then the shape will be provided for the user to recognize. So at the end,
but it's not contemporary to the real usage of the system. So you have to stop.
Yes, how to stop at the end.
But the cognitive tests are usually done in the meantime you're using the system. For example, in prosthetics, what they ask, the cognitive load test in prosthetics, a person walk with the prosthetic system that can be more or less complex, and then is asked while walking on a path to count from 1 to 10 and then from 10 to 1, or residing, because it's a different cognitive load. It's during the usage that should be done. Now, I understand that if you draft these figures, then you give misinformation to the person that is deviating from the real path. But the cognitive test does not imply that necessarily should be done with the same device. It can be done with a different device. It's like talking, that's why they don't want that we talk at the phone when we are driving the car. Okay, so it's a different actions while you are using the system in the same context.
What do we think? What do we thought is that so we use the device to do the navigation, and so why not using the shape during the navigation process? So, but how to use the shape?
But it's the same cognitive load.
Cognitive load, not sure the cognitive load because we didn't test its point.
No, but you are asking to focus the attention and the capacity of discriminated shapes that are provided by the same device. Let's suppose that you have the same device on the arm, and then the one that you use for navigation is on the front. So you have two devices. And the navigation is performed, indication of direction is performed by the one that you have on your head. And in the meantime, sometimes you draw a shape with the other one that is the forehand. And then you ask the person what kind of shape I have drawn. And that one is the cognitive load that you have.
Okay.
It's an additional task that can be actually delivered with the same device. It's not like a phone call. A phone call, it's easy with the same device and see how it works. I know because in prosthetics, for example, if you look at the work of it's not of course our field is not even mine, but I've been reviewed these kind of papers. If you look at the most complex prosthetic systems that they have electrodes in the hand, in the sciatic nerve to restore proprioception. Sometimes they test if the person doesn't have too much cognitive load in discriminating this electric stimuli to give proprioception. And what they do, they ask the person to count or to recite, poetry. In the meantime, he's walking and see if he doesn't overstep or make a mistake. And that time means that there's an embodiment of the system that allows the person to do also any other actions, of course not too complex, and at the same time taking into consideration the cues that you're providing by the system. This is at least, you know, how usually cognitive load tests are run. So imagine, I mean, if you want to use it, just place another of this device in another body part, the same that you tested, for example, and start drawing shapes, eventually telling the person is arriving at shape discrimination, and then you check. In the meantime, they're walking, so keeping into consideration two different kinesthetic signals. Okay?
Yeah, understand. This is quite interesting. We can also have multiple indicators on different arms and the back. Yeah.
So can I go ahead or? You can do it. So the next chapter, the handle for guidance deliberation. So you go give please slide 24.
Okay, 24. Wait.
Okay, so this system here is 2 degrees of freedom or 3 degrees of freedom?
This one is 2 degree freedom for this device. Only.
But if you move the motors, you can also raise them up and down the system, yes or not?
For this version, we have 3 devices based on this, as you can see from here. So for the first 2 here, only it cannot press all this kind of dancing movement. You can only roll it or rotate it. But for
I have a question. So I don't know if you overstretched the 2 pictures, but one seems that has an extension that is higher rather than the second. So look at the one on the right and the one on the left. So it seems that one extends more than the others.
So the dimension is different for these 2. So that's why this one is higher. He says it's a big height. This one is smaller.
So if I rotate all the motor clockwise, the system doesn't go down together.
It's a motion like this, on the surface of the sphere, the workspace. It never goes along the path between the 2 platforms. It can roll on the surface of the sphere, but it cannot
Maybe you have a video, no?
a compression. Yeah.
So this is not, guys. This is not like, for example, the delta device.
No, not delta. No, not
If you
delta.
show the
device.
video, I think on slide 20.
Yes, we have some video here, so you can see from here.
Delta is 6 degrees of freedom. But what's the name of the interface that you have on the knob that I've seen in your office?
The option device.
Omega.
Not the option. It's an omega.
Omega.
Omega is 3 degrees of freedom, no?
Yes. But yeah, the omega is 3, right? The one we have it is also 6 because there is also the resistance, but I mean, without the resistance.
but usually it's 3, so it's 1, 2, and 3.
Yeah. So, yeah.
Okay.
I think, yeah, in also slide 20, I think, I don't know if it's a video, but.
Yeah, and so 20. This one is on in-hand configuration, and also show the other one. So.
I mean, can you go back, please?
Yeah.
I mean, honestly, it's not easy. No, the slide that you had before.
24, right?
Yes.
This one.
Yes.
Okay.
So if I rotate, for example, the first 1, 2, and 3 motors.
No, there are 2 motors.
There are 2 motors. So
There are 2 motors, not 3.
we have 2 versions. The first version, 2 motors. The second version, 3 motors.
So that one on the right, how many motors have?
2, yes, 2 here.
2. Okay, no, then it's 2 degrees of freedom. Okay. If it's 3 motors, it goes also up and down.
Yeah, of
So
course.
it's 3 degrees of freedom.
Yes.
Okay. Then I didn't realize that there were only 2 motors. Okay.
Okay. So.
Slide 29.
Yeah.
So in this case, I mean, the device has a certain complexity. If you compare with this one is a question because let's suppose, well, I want to commercialize this device. Why should replace a joystick on a wheelchair? That is basically a very simple device, but it's extremely robust.
Yes, why putting a joystick? Because we want to use the joystick to control the power wheelchair. Because the joystick has 2-channel output. So when we roll the joystick, like you can control on a plane, a 2 degree freedom. So for the wheelchair to move in this place. So that's why I use this stroke module. That's the idea for this kind of powered wheelchair for navigation. And
this is 2 degrees of freedom, and the joystick there has 2 degrees of freedom.
Yes, joystick, yes, 2 degrees of freedom.
So the question is, why replacing a commercially available joystick with this device?
It's not why replacing commercialized.
Of course, it's an idea. Now, if we don't talk too much academically in terms of research, but we want to commercialize, I mean, there are people from Upsilon here and say, well, I want to commercialize this and replace these crap joysticks that we're using for gaming, and now they are on a wheelchair. Why? I mean, what is the advantage? Because, I mean, the structure is of course, is by far more complex.
So the advantage could be that, for a simple joystick like a controller on the power wheelchair, you cannot apply any force to you. So you can only control it. It's a passive device.
No, there are also active joysticks.
Yeah, some of them.
If you are a gamer, there are also active joysticks.
Yeah, you're
and
right.
They use more or less exactly the same actuators.
For some common ones, they don't have output force. So we use this one to apply the force. And when you put the hand on it, so the device can tilt in the surface workspace. So you can feel the force from it. And the force will tell you which direction all the power wheelchair is going. And is a forward, backward.
But is force feedback used to control power wheelchair?
No, we use the force feedback to provide the direction cues to the hand, to the user. And the user control the power wheelchair through the local module. So it's a loop. So we receive the command from the handle, and then we send commands through the local module.
And what improves in terms of guidance?
Yeah, what improvement? We didn't test the device in the reality, but
this is not important. Let's foresee in the future. And I say, okay, I use this approach on a wheelchair. What improvement in terms of guidance performance? Because then, it's for guidance. What improvement in terms of guidance performance? I mean, a guy that is on the wheelchair go faster, smoother, perceive, for example, what is happening in the surrounding environment. There's more situational awareness. Because, of course, I mean, you give force feedback to provide the feedback. But providing the feedback of what respect to the guidance? Providing the feedback in terms of you should go more in one direction just to match the trajectory or the path that I'm describing to you. So that's the idea.
Okay, the advantage could be for some specific people, that have some misfunction of the hand, so that they don't have like a stroke or something like that, so you cannot move the hand. But by placing the hand on the active device, it is more possible, it's more possible or more likely for the user to receive the command and to move the hand. For somebody with the stroke on the hand, they cannot move, but I also want to control a bit with the movement of the small
you don't want a stroke that use the parametric hand to move a wheelchair. Usually they use the non-parametric hand.
Okay. It could be dangerous, right, for this kind of...
Parametric hand, it depends on the level of disability, but it's not the one that is used for controlling a wheelchair. They use the side, the hemisphere that is intact. So if it's damaged the left hemisphere, the right part is gone, and they use the left hand.
Okay, so, that's the case. Yeah. But still a lot of things worth trying on this for different applications.
No, I will use the same system just to use the force feedback to control in terms you go outside from the path. So if you drive your wheelchair and you're going in one direction, and eventually there's a vision detection of an obstacle, the system will force the hand or give feedback to decrease the speed of turning on one side rather than the other side. This one is how I would use the force feedback. It's just a joystick that is telling me decrease the velocity, turn back right or left. But it's not, in terms of assistance. It's in terms of haptic cues. Because basically, it's the same concept that you are using for the first experiments in the first chapter. The system for giving haptic cues that are not force feedback, but are stretch of the skin. Yep. In such a way, the person correct the trajectory and decrease the deviation respect to the desired path.
Okay.
Slide number 41.
Yeah.
Here more as a philosophical question. Do you really need this degree of redundancy in terms of actuation?
Degrees of redundancy.
So, you have 4 motors basically to generate 3 degrees of freedom. Am I right? It's X, Y, and rotation.
We have 4. Rotation and folding. We have 2 pieces and for the end effector. The end effector is more than this.
Yeah, but this.
We have 4. So the end effector can rule as a.
No, it's not the end effector that changed there. You are changing the configuration, but the position of the end effector remains the same. So there's a degree of redundancy there that is not actuated at the level of the end effector, if you want. You change the internal configuration of the joints.
Yes, from this part, yes, but in general, what we perceive from here, so we get another one. We say is another degree of freedom.
The 4 degrees of freedom is used to change the shape of the end effector. For example, you flatten it and then you press. Yeah. But you are not. But you are changing the internal configuration of the kinematic chain.
Yes, kinematic chain.
This is what I've seen is the main usage of adding let's say a 4th degrees of freedom, a 4th motor, a 4th joint, because with 3 you can give basically more or less X, Y, and rotation around Z. Am I right, or I am making a mistake in terms of calculating the degrees of freedom, Claudio?
No, but it's correct what you say. So the 4 degrees of freedom is to change the local shape of the end effector at the palm. This was, of course, one of the objectives, because also later on, and then we changed the end effectors. So this was what we had to do. But of course, if you remove a motor, you can keep the 3 degrees of freedom without the folding action.
And
probably, probably I would put the motors probably in a different way then.
No, I don't think so. That put the motor, but I will introduce the rationale behind, let's say, with higher strength. So I say, okay, we have a system that can move in 3 degrees of freedom, plus we can change the configuration of the end effector, just written like this in red.
Yeah, that's better.
Because it's the same. Let's say, it's the same problem with the previous slides. So strong statement. So what's the novelty? That you can basically reconfigure here the shape of the end effector, and usually the end effector never change the shape.
Yeah.
Because this is what happens in haptics. Mostly you have end effector is that one, right? You grasp and then you have the degrees of freedom. Here you are reconfiguring internally the kinematic chain in such a way to reorient the end effector, and that's the main novelty that you have to stress in front of the audience. Okay.
Yeah, we described in application-based view on this. So in general, it's 4. Yeah, that's right.
Last question?
Last question. I know that it was arriving. $58.
Yeah.
So here I have also here the different condition you have to describe much better. And another thing, sorry, slide 57, because this one otherwise would be too long and I would be kicked out from the audience. So, okay, but no, 57. So this problem in the confusion matrix, for example, the 60% that you have in the classification at U, the position, the component U.
Yeah.
Do you think that the problem that you have here is that when you activate one part, there are structural vibration of the system itself, and then people, vibrotactilely speaking, they get vibration from all over the structure?
Yeah, that's the case during the experiment we did. So some cases, some people cannot recognize where the vibration comes from and why. Because this part, all the haptic modules are rigid. So when 2 rigid part connects to the central spot here, the vibration will be transmitted to all the
structural vibration.
Yeah, structural vibration. Yeah.
I finished.
Thank you. Thank you.
So, Nathanaël? Yeah.
Yes. No, you can continue at lunch.
Rennes is looking forward for Lisheng.
Nathanaël?
So thank you very much for the presentation, and thanks for the invitation to this event. I'm impressed by the amount of experimental work that has been done and the numerous engineering development that have been done. I have made a few remarks in my report about sometimes like the fact that maybe having an application in mind will allow you to define specification at first, and then in the end you could compare what you got as performances with respect to what was expected at first, based on the application constraints or the state of the art. So, but there's a lot of work that has been done. So I have a few questions, like not always associated to slides, but I was wondering, for example, going back to the beginning, when you work on your 2DOF forehead interface, there's a spring that imposes a force amount over the skin. How did you manage to find the right spring value? Did you try several? Because like basically changing this spring value may probably transform the entire results that you had. And so, did you adjust that to the perceptual threshold of the participants? Did you choose it not to like level big marks? Because like maybe strong spring would have increased a lot the recognition performances.
Yes, for different users, the spring, the force from a spring should be different, and we adjusted it from the beginning in the pre-training of the experiment. So how do we do it? We have a small part here. So by adjusting the distance between these two parts, the spring, the theta. So the distance, the displacement with spring can be changed so as to change the force.
Okay.
So
was it tuned for each subject?
It's tuned for each.
Always the same.
Not always the same. For each subject, we adjust the device at the beginning, at the training session, and we ask the participant if he or she feels comfortable or reliable on this. So we test it at the beginning.
So for each subject, there was some adjustment to the stiffness of the spring.
Yes, that's what I did. Yeah.
Okay, good. That's something maybe I missed in the report, but it's important maybe to speak about it. I was wondering, you were speaking a lot about like recognition, ability of controlling the shapes, the positions, or the forces of your interfaces, but you rarely speak about bandwidth, and you're mostly relying on servo motors that have quite limited bandwidth and velocity control abilities and stuff like that. So you do not test in your experiment like the effect of drawing the shapes at different velocity. Do you think like how good is the bandwidth of the systems you have been using? Because like for haptics rendering, bandwidth limitation is quite critical, because like you can move from proprioception informations to haptic or vibration, and here you are probably quite limited in terms of dynamics.
Yes. The performance could be different if we use different actuators. Now we use some motors, because some motor for this case is well enough. Mm-hmm. So you can actuate the device with the acceptable speed and force.
And for example, when you draw a square, how long does it take to draw a square in the experiment was done? Is it something instantaneous?
Yes, for the shapes, for each one we use 3 seconds for each.
So it was like 1 second per displacement, like
yes,
that?
3 seconds for each. So it depends on how the motors work.
And do you think that like making it slower or faster would have like, I don't know, maybe slower is more difficult to perceive, maybe faster helps sometimes to feel the movement direction? What do you think would be the effect of changing the velocity of drawing the pattern?
Yes, the velocity also matters, also makes a difference for the result, I guess. If it's too fast, it's not easy for the people to recognize the shape. And if it's too slow, as you said, I don't quite memorize what is happening just a few seconds before. And we choose 3 seconds before, because I did a pre-test on myself, yes, before the experiment, and also based on the capability of the motors. Okay. You can only move with this speed. Yeah.
Okay, thank you. And one thing to be sure, like this is a 2DOF interface, and as Lorenzo said, to do the guidance in free space as you did, there's only need for 1 DOF in a way, the direction of the displacement. how would you have ideas of how to use 2 degrees of freedom to guide better the subject in a 2D or 3D space?
Yes, we thought about it during the experiment before. So the other degree of freedom, like up and down, could be used for guiding the user to climb a stairs, like all across a collision. Like we have a box before, so the antifact can move up to tell the user to go a bit up to a state or something like that. Yeah.
Okay, thank you. I'm switching to the chapter 3, so it might be the one on the 2DOF interface. Around this one.
Yeah.
I was wondering, like, you're speaking a lot about haptics, but in the end, the displacement of your handle is quite large, and it's not clear sometimes if the hand of the user remains over the handle and move with the handle, then it's like proprioceptive guidance or kinesthetic guidance, while if the hand is fixed and the handle moves, then it creates like haptic stimulation. So I was wondering, what was the initial purpose? Was it like something to interact at the haptic level, or both, or?
Yeah, from the beginning, the objective is to design this kind of handle for powered wheelchair. So for this kind of application, skin stretch is not quite reliable for some situations. So that's why we use a combination. It's a combination here, combination of skin stretch on the pen, and also the kinesthetic force applied to the whole arm. So with this combination, so when the device starts moving a bit, we can feel the stretch on the pen. And with the force, we can know it's a larger motion. It's a larger motion for more directional information. Mm-hmm. So it's a combination of that.
Okay. Also one thing about slide 29, but we discussed that quite a lot. Like in the end, having a separate rocker joystick to read the input and then using the handle to provide back some feedback is quite complex with respect to like a back drivable haptic joysticks, on which in the same channel you could both apply forces and read the intention of the user. So you were discussing in the report about like implementing some impedance control could be easy on such a system. Could you detail a bit more how would you do impedance control with a non-back drivable handle and and an input such as a joystick, like a rocker, because it looks like more like admittance rather than impedance that you can do with that.
We didn't compare these two situations. We didn't compare to design, but this one has the advantage like the joystick is easier to control, so we don't feel any impedance from the whole device. We just follow. So we just follow. We don't apply any force to the handle and to the whole system, but only control the rocker module with the small finger here. So it applies or requires less effort, I would say. So we don't need to very high force load to apply to the device to bend it to any direction.
At the same time, it's quite complex because like your finger is driving the system, providing input, and then the feedback that you may use to servo your control is coming back to your hand displacement. So it might be quite difficult maybe to integrate because like it's acting on a different channel than the one you perceive. So I mean that would be interesting to test later on probably the disconnection between providing input on one joystick, feedback on another one to see what it creates.
Yeah, we can do in the future for the experiment on the powered words. Yeah. So another curiosity questions. I see that there are lots of developments and sometimes you don't really know what it could be used for or what information could be provided with that interface. On the extension of this work, when you adjust the shape, do you have any idea in mind, whether with soft or origami, of how and what information would you encode
through this shape changing in the context of a navigation application?
For this device, we didn't use it. We are not aiming to using it for navigation. We use it for in contact ambient interaction, which means we contact with the surface of the end effector. For example, the soft one, when it changes curvature, we can feel from the surface. It can create the sensation of interacting with the object like a water blue or water damping surface, so we can feel the curvature from it or the shape from it. It's not for navigation.
Okay. So an encounter for you is not a matter of the interface coming to you, it's rather based on the fact that you're going toward the interface.
It can be integrated in virtual reality. For example, we have some virtual object, then we detect the position of the device and the position of the hand. So whenever the hand moves to any position, the device will follow the orientation and the position to generate the force to the hand. It's not like the hand will follow the hand.
Since you only have two dots, you can control the orientation, but not like really control the collisions or the interaction. Really, it depends on the user movements to generate the interaction.
Yes, for the grounded configuration, yes, because the device is attached to a table or something, and because the device needs a configuration. But we can also use the device with a manipulator like a robotic arm. So with a robotic arm, you have more degree freedom, can move the device within the workspace. That's the other future application on it. Yeah.
Okay, thank you. Now, like maybe to finish some questions about the chapter 4, it was on the 4 DOF interfaces, and I do agree that so you did quite a lot of characterization work in the report with looking at the Jacobian. Sometimes you struggled in some weird complex notation, and I was wondering there's a lot quite important part on the ellipsoid manipulability calculation. Where you characterize the manipulability properties of your system, and in the end, there's no real consequences of characterizing that. So, what would be your conclusions based on your analysis of the manipulatory ellipsoids? Apart from the fact that you can control well the force direction and the orientation of your end effector. Why was it needed to be as precise? What do you have in mind that could be done thanks to a manipulator with such capability?
We did the manipulability in the simulation. So we use MATLAB to do the simulation. We just to find out that with this kind of numerical simulation, the device is capable to be manipulated. Just the proof of concept in simulations. But in the real device, we didn't do the real manipulation on it.
No, my question was more about thanks to this specific property and controllability that you have, does it open new possibilities of doing specific force orientation control when you're applying feedback or some stuff like that other interfaces could not?
Yes, it can help to understand the control of different end effectors. Yes, it does. Yes.
And maybe one question about specific when you assessed this interface, I was a bit surprised and I did not understand. You selected different X and Y and alpha and theta that you send to the users and to try to again discriminate. And what was surprising me is that you have the better performances in subjects detecting changes in theta. That is quite not of use with respect to alpha. I don't remember. It was in the report at some point. You asked people. Yeah, people were more good at detecting. Actually, I'm surprised by the fact of seeing theta there on the graph C, because I thought theta was on some other figures. It's not placed exactly there.
Okay, so for this one, it's theta for the roll motion. So we change the orientation of the end effector, and in this case, the end effector is regarded.
That's still a function of the theta that you have on the other figures, but how do you explain that people are better at recognizing theta rather than alpha? I would have thought that like maybe the sharpness of the edge would be easier to get than the orientation of the edge in itself.
For this, I guess it's because that we have the edge, but the palm is a flat surface. So when we attach the edge, so we attach a certain line of the edge. So even when the end effector is folding or too much or too little, we don't feel much difference between the edge, between the angle. This
will feel like more surfaces coming close to the palm.
Yes, when the angle alpha becomes super big, like close to a flat, yes, it's a surface. Mm-hmm. But when it changes between 0 and 15 degrees, mm-hmm. It's not quite easy to recognize. Yeah.
Okay. And do you think that like there's no mention of the forces that were applied, and based on the forces, like due to the compliance of the palm, the kind of like feeling would be quite different? Did you assess like differences in applying strong patterns or weak patterns with the interface? Because you were speaking like you can apply up to 2 Newton, I think, of force.
Yes, based on the calculation from the motors, yes, could be 2 Newtons, but it depends on depends the parameter of the different subjects, because the palm is like a form, as you said.
It's like when you place the edge, do you try to like penetrate into the tissue, like because you place the X and Y position rather at the surface, or there was a threshold like you kind of touch as the subject, like does it touch and then go inside the millimeter, so it's really into the skin and the tissue, and it makes it easier to feel? How do you ensure that like there was always a contact?
Before the experiment, we do a kind of calibration for the device. Mm-hmm. We define a 0 point, like the very contact, the beginning of the very contact point, and this we define it as a 0 point.
So this was meant that at the 0 point, the simulation was a 0, not like pressing a bit into the pan.
When it goes higher than 0, it means the device is going deeper to the pan. So applying, so as we said, the vertical displacement.
Yeah.
This means it's going higher.
But when you were testing theta and alpha, you were at the 0 point. You were not like a bit along the Y inside the pan.
It's almost 0 contact. It's not getting any higher. Yeah.
Okay. Thank you. And maybe the last question. It's not. I was wondering, like, if you could tell me a bit more about, like, how does the VR drive the stimulation in the slide 53?
Yeah.
Or the 52 maybe with the visual system. So basically, in the VR, what was driven, like the shapes, but also the orientation of the edge was controlled, so that like it seems that the participants only do up and down. They don't have on the video. They don't explore the shape of the robot, of the virtual object. Was it a constraint of the protocol? Were they allowed to like do tracing the object?
So the end effector should be changed for different objects.
Sure.
And we didn't explore because it's a proof of concept to evaluate.
Even with one provided shape, like people were just like told to go up and down toward the object, not to go around the virtual object.
Not to go around, just up and down movement.
Okay. Thank you. I think that's all for me. Thank you for your presentation.
Thank you.
Thank you. I look forward to Christine. So thank you for the presentation. I was very impressed by the quantity of work that you have done and the quantity of device that you have tested. I understand that you have designed and built all the device into the case or not?
It's okay or not? It's a big question. Sometimes it's not okay. Sometimes it's okay because mechanical science is not always easy because it means this, right? It means the work on the designer, right?
Yeah, so
If I understand correctly.
you that really worked most, so if you are the person that worked mostly on the design and building of the devices.
Yes, building, design is not easy sometimes, otherwise it's not difficult.
But you do it.
But
But you do it or not?
Yes,
My
but
question is, do you do it?
but I did it, yes.
it was
Yeah. So I'm a mechanical engineer, so
Okay.
so I did all the
But
stuff.
how do you choose the design that you build?
How do I choose? Based on the applications and the objective we start from the beginning. So if we want something to provide to provide the kinetic feedback, we think about what kind of component we can use to generate this kind of force. And based on this, we chose the parallel mechanism or serial mechanism to generate this kind of actuation. So this is the idea from the objective and from the application, and we go to the design considerations.
Yeah. Try several times.
Yeah, try several times and modify.
You have changed because you do not explain really in the thesis. You do not explain what is the initial objective, what is the characteristic that you want, and how you come to this shape. For me, it was not so clear. Sometimes, and you have many collaborations, so maybe sometimes it is the design device that has been defined by your collaborator. I think that you have to, it will have been better to more emphasize on this part of your work that is probably time consuming. For the second device, that you use, the parallel robot, it is not so clear for me how you have choose this device, because so this device has been presented by other people in IRISA paper, and in fact for me this device has theoretically there is no mobility. There is mobility only due to some deformation of the design, which is in 3D printing. Have you observed a difference between the device which is higher and the device which is larger?
Okay, so the design of this is a very wide use. It's designed about 40 years ago. It is used on the shoulder joint. So it's a very well designed mechanism. And how we compare the difference? So as we can see now, when the dimension is different, the force and the workspace of the device would be also different. So based on this kind of difference, we can use for different, we apply more force, we apply a larger workspace. So the dimension makes difference to this. And, sorry, any more? Am I answering correctly on this?
And
Okay.
so for my understanding of this device, the mobility comes from the fact that we have three lines that intersect. And I believe that it is easier to have this property for the higher device. Do you observe that you have it is more easy to move this higher device or not?
Based on these two, yes. The higher one has a larger workspace. It's easier to rotate, and that's true. But for the smaller one, the diameter of the surface is getting smaller, so the workspace is smaller. But to move it or to rotate it, to rotate rolling it, it's not getting more difficult.
It's not mechanically more difficult.
It's not getting more difficult. It depends on the smaller one or the bigger one. Smaller one is also easy to rotate or manipulate it. Yeah.
And what was your real objective when you design? Why do you choose parallel robot for this task? You want only to move in two directions. Why not parallel robot?
Because a parallel mechanism applies a high torque and zero one. Zero one, if you have two motors and the zero change, the motor needs a very strong structure and a strong force to apply the force and the end. But with the parallel mechanism, you can apply a very high force and can support a very high payload on it. That's the question also for the difference between the serial mechanism and the parallel mechanism. And the parallel mechanisms have this kind of advantage, just as I mentioned, high payload and faster dynamics compared to the series one.
The next device,
yeah,
that is for this one. Have you studied what is the influence of the size of the modules, and especially if you have an arced link? Does it change something? How do you choose the dimension?
I will choose dimension based on the dimension of the hand. So we use the articulated link to go through. It's like a ramp. It's a very like a ramping link that goes from the back of the hand and go to the other side of the pen. So we didn't use straight link because you need more space and you need the upper platform bigger than the current one. We use curve link to make the device smaller and make bigger workspace on it, based on the size of the pen at the hand. Yeah.
What is the application that you have in mind when you define this several end effector?
Which one?
In this case, you have a 5 end effector.
Yes.
Why do you define this? What is your application? What is the application that you have in mind?
Okay, in my application, the first one is the rigid one. It's the hinge-like structure. They can generate rigid edges and surface. So for example, when you're interacting in VR with a virtual object having an edge, like a table or a flat surface, it's good for this kind of virtual object. And the second one is a reversed flexible U shape. It can generate curvature from edge, flat to curvature, and it's soft with some damping stiffness on it. And the third one is a elastic structure with it can stretch and draw. So this could be used for you interacting with a surface like a blue, like a surface of blue. So you feel different stiffness when you press or not. This is for that application. And for the third one.
Yes, but what practical applications?
Practical application, just as I mentioned, could be used for the interaction with the virtual object in virtual reality and the immersive virtual reality as the application. Interacting with the virtual object to recreate the artificial touch on this. Yeah.
Okay, so, but you have not tested on this kind of application. For example, we had an application where we work with Maud Marshall, where we want to see what is the shape of part of a car. And maybe this kind of device can be well applied because the shape is not necessarily flat. And have you tried to envisage more complex tasks to see what is the behavior of the people?
We didn't try yet, but it's a very nice application for the future. We can use for the second one because it has different curvatures. It can also generate a flat surface. It can recreate sensation or touching the edge of the car. It can be used for that. Yeah.
Yes, I think it was with this one. It was in the slide 51.
Yeah.
In this slide, I understand that the conclusion was that the objects that are not easy to identify was the object with curve. In this case, do you believe that it is linked to the fact that with your system, when you change the shape, you change also the stiffness of the system?
So do you mean for different virtual objects we change the end effector, right?
When you use the end effector, which is soft, and you can change the radius.
Yeah. Yes.
But when you change the curvature, I believe that you change also the stiffness.
For the second one, the U-shaped one, when we change the curvature, the stiffness depends. But I would say 100% correct, but it depends. If we move the two arms closer to each other, the top of the sphere is getting getting more stiffness. But when we stretch out, making a curvature with bigger radius, the stiffness could be smaller. So it depends.
Not sure we change the stiffness, so unless you really go very close, and then you really kind of have a, the configuration like this. But when they are a bit far away, where usually this is how we use it, it changes mostly the curvature more than the stiffness. But there is another end effector where we change the stiffness, the elastic one.
Yes, also depends on the materials and how do we arrange it. Yeah.
How do you explain that this case was not so well identified by the people?
Okay. So we divided the objects into 3 groups. And for the first group, the objects are rigid. So it is better for the first end effector to recreate the sensation because the end effector is rigid. We cannot generate a rigid sensation with a soft material, right? So that's why for the second group with the object with having different curvatures, and it's better for the second object to render because second end effector has a curvature shape on when we control it. So this also explains that for the different virtual objects having different characteristics, it's better to use the appropriate end effector, like the rigid one for the rigid object, the soft one with the soft end effector. So this could be the idea also for the modular haptics. We choose the appropriate of the correct end effector for the appropriate virtual object to render. We cannot render a blue with the rigid one. It's not quite easy. Or it can be done, but it's not. It cannot be very well perceived. That's my idea for that. Yeah.
So, if you have to build if you want to build a startup, which device do you want to sell?
To sell. It depends on which one is more expensive.
But you have to find people who want to buy it.
Yeah. Anyone pay more money for that? I was anyone for the. Yeah. Okay, it's a joke, but I haven't thought about it before. But depends. For anyone with the more performance could be used for that. But I would prefer for the final one. It's my favorite one for this because it's the handle. It can be used in the bottle wine gaming. You move a wine through a loop. It can also be used on the wide cane. The cane for the visual blind people. It can generate navigation cues like left, right, forward, backward. It is quite, I would say, quite easy to be customized.
It's the simplest also.
The simplest also. It's easy to use and shape like with a very interesting shape. You hold something. It's easy to be adapted to for the integration on the wide canes or workers.
Thank you.
Thank you.
Thank you. So I will continue with your professional. So thank you, Paolo and Claudio for having invited me for this defense. And thank you, Lisheng, for all the work that you have done. It was really a pleasure to hear you, and I had the chance to discuss with you several times. So it's the final step of your work. So I appreciate to be part of it. And as the other members of the jury, I have to underline the impressive number of devices that you designed and all the experiments you performed. This is really remarkable, I think, so it has to be underlined. And it covers a large spectrum of potential applications and potential domains, so this is very, very, very interesting for that. And I have to say that you was a member of the Dornell project that Claudio and I are leading, which is about designing a haptic envelope for people with disabilities for navigation application. And so you you discuss also with the clinicians, and I have one question regarding that, and perhaps to also have an answer for Lorenzo, I don't know. If I remember well, you presented the kind of mushroom and the steel platform, I don't know how to say, to clinicians, and they try it. Or did they try it in Nantes, if I remember well?
The mushroom, not yet.
Right.
The previous one.
The previous one. And
Previous
so,
two.
what do they project as application for navigation purposes for people with disabilities? What do they imagine the way they can use it for people with disabilities?
People didn't try it, but I bring it there to show to other clinicians. Yes, that's all the device. Yes, we have several ideas on it. The first one, they mentioned something like how to change the dimension to make it adaptable to a powered wheelchair, and how to change the actuation according to the application scenarios, like for the powered wheelchair. And also, they mentioned something like using different materials to make the device more flexible and more shapeable. They mentioned something like this. And this all was trying in the future if we do some experiment on it. Yeah.
So they are able to imagine that there are real applications that can be designed for with your device. So this is really important. I mean that what you have done is also inspiring other applications for clinicians. So I have some perhaps more precise question. I had the same concerns about the forces and so on, so I dropped my question about that.
Oh, sorry.
That's cool. And regarding the, for example, the device on the forehead, I was wondering, is there the sensitivity equally spread onto the forehead, or is there some differences that can explain the fact that you perhaps perceive more or less shapes?
Depends on the subject. Also depends on what kind of forehead they have. You know, someone has a flat forehead. Someone has a forehead not super flat like me. But also depends on that. Also depends on how people perceive the stimuli. Some people perceive better than others. They can feel the small difference between the two stimuli.
Mm-hmm.
So this can be said depends on the people's perception capability. So this is the case could make a difference for the performance and for the evaluation of the device. For the second part of that. I don't remember what I said, but in fact, the question is, okay, you have some individual variation of perception. Yeah.
And how can you imagine to calibrate, in fact, your solution so that it matches with this variation?
Okay, it's for the variation. Yeah, we did a pre-taste training. You know.
For each individual?
Yeah, for each subject we did a pre-taste, and this helps the subject to memorize the most comfortable force applied by the pin and the most recognizable force experienced by the device. So we did a calibration for each one.
And I have the same question, more or less the same question, on your slide 26.
Yeah.
Was with the structure, yeah.
Yeah.
And here, in fact, you have some confusion between the most large confusion is on for straight on the sagittal plane or diagonal. Yeah. The diagonal motion is not so much recognizable. And is it because only that people are there is a great confusion because of the device itself or of the amplitude of of the motion, can it be compensated by augmented the magnitude of the motion? So
Okay, for this, I guess there are two reasons for this. First one is that we use the hand to move left and right. Maybe we are more familiar with this kind of left and right, forward and backward. But this is one question, and one reason for that. The other one is that when the subject uses the device is put in front of it, and the subject put the hand on the panel or the chair. So the left and right is more easier to recognize. But the diagonal one, the northwest or northeast, it requires the device to move a bit forward or backward. So this might make these two patterns more difficult to recognize. I guess it's because of this, but we didn't compare the.
You mean that perhaps if you have placed the device not in front of the people but on the axis of the arm or the shoulder, the perception will be different?
Could be because how we recognize the pattern applied or the kinetic force applied to the hand, we compare the relative position to our human body, to the whole body here. So if the device is put here, so it means we need the subject to move the device to move the hand in the other place. So in front of the very in front of the device make it easier to recognize, because we said kinesthetic sensations is about the position. It's about the information about how do we receive the force in the neighboring body part, and we use this kind of feedback from the body part and the muscle and the joint. If the muscle and the joint are placed in other positions, the result could be different, I guess. Yeah.
And so the idea, if you imagine to have not a symmetrical motion activation of the device, but you have larger motions in diagonal and so on, could you imagine that it will enhance the performances?
Yes, I guess it's larger workspace could make the result different, and probably larger workspace could make the recognition rate higher because we move the hand higher. Just like a screen stretch, you degrade down the displacement, you will decrease the recognition rate. You increase it, you will increase your recognition rate on it. And it makes a difference, I guess.
Okay. I have one question. So you, if I remember well, you characterized the force for the elastic rubber, and only for this one.
Yes, we do no, we didn't show it here. We did one force calibration on the elastic one, because we want to know if the stiffness on the an effect would make a difference for the panel. So we calculate the force. Then we know how much force we can apply by manipulating the two arms. We didn't do the other one because of what? Because the other one is more rigid, okay. And this one is more soft. Because of that, I guess. Yeah.
Okay. And can you imagine to have this model, thanks to the model, you use it to control also the force that can be applied?
Yes, it can be applied. Depends on the dimension you use. You use the bigger one. We can use the same method or the same way to calculate it. And if you use the same material, you should use the same method. But depends. If you change other materials and with the other force or with the other device, the result cannot be all the same. Yeah.
I have also a question on slide 33. And the other one. 33. Yeah. Can you make it move? So there is a video? Yeah, play it. Yeah. In fact, I have one question. I'm not sure to see exactly what If I imagine the protocol, so the experiment you perform here, you apply motion, you stabilize your platform in one position, and then you stretch the platform. And there is I have the impression that it moves. You stabilize it, you open or close the arms, and it induces a motion onto the legs. Is it only an illusion, or is it true?
It's true. Yes, if we call spiral cam. When you rotate the spiral cam, the height of the device will change. But what doesn't change is that we can always measure the center of the upper platform. And then with this position, we can always know. We can also do it in the kinematics and with some insight, and then we calculate kinesthetic analysis on it. So it's controllable. It's always controllable. Yeah.
So it's one important thing really interesting.
Yeah.
This controllability. Yeah.
Yeah, it's always controllable.
And I have just one last question. What are you the most proud of? You design too many devices, so much devices. And what is the devices that makes you proud?
Wow. It's a big question for that. Someone says, I would say the whole work of it. It's like a trial and a test. To try what can we do on this based on this kind of mechatronics, and we test how our device will work on it. So based on the trial, we know which one performs better on specific applications and the simulation we want. So it's a trial. And how do we evaluate it? Which means that based on a specific design, based on this kind of evaluation, we will know in the future for different design, but on the similar routine, how do we evaluate it and how do we use it in the application? It's a whole process, but which one is more powerful, I would say, also the last one.
Okay, thank you. Thank you for the answer. And,
yeah, I can say something.
Okay.
So I don't have questions. So we will eat at 12 o'clock. No, I really want to congratulate Lisheng again for the work that you have done. I have to say for the jury that Lisheng has been a student, I would say, very, very autonomous, self-motivated, always serious, with passion, hardworking. We really, helping, of course, in advancing, but he did a lot of work on his own, which is quite remarkable. And also when he started really at the beginning of the hard COVID lockdown, the first one, not the first one. So when really we had to stay home and not go out even just for a walk. And so he spent the start of his PhD in these conditions, which was very, very complicated also because he was coming from abroad, so in a foreign country. Congratulations also for having survived this very complicated time. Yeah.
Thank you.
Yes. Yeah, so first, of course, congratulations on the work that you have done until now. And yes, as Paolo said, I wanted to highlight the resilience of Lisheng. So Lisheng, before he was at IIT in Genoa, as an engineer before coming to France. It was really at the beginning of, it was January 2020. So to get his visa to come to France, he had to go to China, right, to get the visa. So that was the time where in China there was already the first COVID, but not in Italy yet. So when he came back, he had to isolate for 15 days, due to the rules. In those 15 days, COVID came to Italy, but not in France yet. So when he came to France, he had to isolate 15 days because of the rules for people coming from Italy. After 15 days, it was the first day of work, it was the first day of lockdown in France. And so he was stuck, let's say, so he was stuck for at least 6 months, really in very hard conditions at the residence at IRISA. And so, of course, also with respect to the work, of a mechanical engineer, not because here we really had no access at all. So I remember we did the first meeting with Marco in a park nearby in Plan de Vaux. And it was the time I remember that here we were not able to find masks. And so Lisheng from China brought a set of masks. And so we discussed a bit what we could do. So we started to work on a review paper, right? During the COVID, we have seen a great amount of review papers. But then, of course, it was not the best condition to start a PhD. So, all the work that you have seen, it is basically done in 2 years, 2 years and a half. So very concentrated, I would say. So, so this part of his work and the resilience to all these difficulties, of course, it's something to highlight.
Thank you.
Thank you.
Yeah.
Thank you, Paul. So it's time for us to leave for the discussion.